Good morning, ladies and gentlemen. I hope you are well at your houses, you and your families. This is Mr. Waters, and we're going to have, we don't have much more to do with our calculus study this year. There's always more that we could learn, believe me, but we're going to have 2 or 3 more lesson sessions, as I mentioned in my announcement. Okay. I have all of your tests, of course, and they're in the grading lab, and by the next time we meet, your test should be fully graded and ready to go. Okay? All right, so anyway, so we're still working with integrals, and now before, the chapter 5 had specifically to do when we were calculating integrals, we were calculating areas under curves, right? And we developed in the beginning some vague notion that calculating the area under the curve of a function f was related to the antiderivative of f. Okay, so let's go back, and I want to go back and remind us of what the antiderivative was. So in this chapter, what we would do is we'd connect the fact, besides the fact that the area under the curve of f is equal to capital F, right? That is equal to capital F, that the area under this curve here, right, is equal to some other function, capital F, right? And we developed vaguely, although we didn't prove it, we developed vaguely that f primed is equal to f. That is this area curve, which was the accumulation, the sum of all of, whatever f was, right? We had vaguely that this idea was f prime, that f was always going to be the derivative of, little f was always a derivative of capital F, or that f primed, capital F primed was equal to f, right? And we didn't do much with that, right? But we noticed that it was true. So the idea is that if we're starting with capital F, we calculate a derivative to get to f. But if we start with little f and we work backwards, we're calculating something called the antiderivative, right? So now we know a little bit about that because I spent a little bit of time with power functions at the beginning, right? And we also mentioned the fact that we could do some direct antiderivatives, that if I knew that the derivative of sine was cosine, then the antiderivative of cosine would be sine, right? Just working backwards. There's, as it turns out, a little more to it than that. So, but that's kind of the general concept. And not only that, calculating those antiderivatives also gave us the areas under these curves, corresponded to the areas under the curves, which is what the fundamental theorem of calculus was about. Okay? But anyway, so here, this is true. So what I'm saying is this is true here. If we have the derivative of x squared is equal to 2x, then the antiderivative of 2x has to be equal to x squared, right? Working backwards. So, but it's a little more complicated than that. Because imagine, let's say we've got several f's. So let's call it f1 is equal to several capital F's. Let's say that's x squared plus 1. Capital F2 is x squared plus 2. Capital F3, let's give it a negative, x squared minus 4. Capital F4 can just be plain x squared, right? You can see that using the rules of derivatives, if I started with capital F and took the derivatives, we'd lose all those constants, wouldn't we? Because the derivative of a constant is equal to 0. So if we took the derivative of all of these, they'd all work out to be 2x, right? So if we're starting with 2x, how do we know which one of these that we're going to be working back with? Well, the answer is we don't necessarily. If this is literally all we know, if we know that we're starting with 2x, then there's no way to know exactly which x squared we're working with. So what we would typically do is, we would say that if we're starting with 2x, the antiderivative is x squared plus some constant c, which corresponds to one of these positive or negative constants or fractions, or could even be 0. Okay, does that make sense? Now, we might be able to tell each of these if we're given something about the about capital function f. For example, if we knew that f of 0, if for some reason we knew that f of 0 was equal to 0, well, that might allow us to pick which one of these is correct, because we would know that, okay, f of 0 is equal to 0, so that means that x squared plus c itself, where when x is equal to 0 would have to be equal to 0, so that means we'd put 0 in plus c is equal to 0, so that would mean that c is equal to 0, right? So if we knew that was true, then we could work out the fact that our original function is equal to x squared. Or if we're given, say, that f of 0 is equal to 4, let's say, right, if we knew that, okay, we could say that, okay, that means that x squared plus c is equal to 4 when x is equal to 0, right? So that's when x is equal to 0, so we put 0 squared in, so we get that's equal to 4. So in that case, if we're given at the end that this function value here at 0 is equal to 4, that would lead us to the idea that f of x would have to be x squared plus 4. Okay, does that make sense? I hope it does. Okay, in the world of math, those are called initial conditions. And they're very important later on, a topic that unfortunately we're not going to have time for this year because of our coronavirus break, but the solving of what are called differential equations. Often start with, in order to get a particular solution to it, we have to start with an initial condition like that. All right? Anyway, so that might be a subject of further study for you guys later on in your academic careers, maybe in college. Okay? Anyway, so that's the idea here. So this is the concept I just want you to show first off, and I'm actually going to stop this video right here because we're going to jump into another topic where we're going to look at antiderivatives. This is looking at antiderivatives kind of analytically, and keep in mind, whenever we take an antiderivative, whatever it is, we've got to end with plus c here, unless we're given an initial condition that allows us to calculate what c actually is. Okay? All right, very good. So that'll do for this part here. And the next part is going to be about calculating or working and deducing antiderivatives graphically. All right, starting with graphs. All right, and more about that in the next video. Bye.